share my slides. Can you all see my slides?
Yes.
Okay.
Yes.
Wonderful. So thank you all for coming to my pre-research advising presentation. My name is Shiv Mishra, and I'm a professor in the computer science department. And my contact details are listed here in this slide. My office is in the systems lab. The office number is ECCR 1B22. And if you have not been to the systems lab, and once you find this place, then you know that you are very well, oriented in the engineering building, know that. Email is the best way to contact me. Just send me an email and I typically respond within 24 hours or so. And then some of the details about my research are included in my webpage, but my webpage is not constantly updated. Probably I will update it once a month or something like that. Okay. So the goal of this presentation is essentially to provide an overview of the type of research that I'm involved in. So I'm going to be talking about some of my current projects that I'm doing right now. And I'm always open. In fact, I'm always eager to hear from you. Any ideas that you might have, like any, and your ideas don't have to be mature, any preliminary ideas that you have, please don't feel free to just, talk to me about those ideas. Okay. So my research overall, and hopefully, this presentation will provide, convey some, a direction that my research direction that I'm trying to pursue. Okay. So, okay. So my current research is at a high level, it can be broadly classified into two different areas. The first one is what is, traditionally called systems research. And my current focus within that systems research is system support for, Internet of Things. And then the second area is what is called social computing. And so I'm going to be talking about some research projects. And again, I'm trying to, put some of these research projects under different categories. The first one I will talk about would fall within system support for what is called edge computing. Another one will be what we call as cyber safety. Then third one is, democracy and technology, and then socio-technical systems. And I will not have enough time to go into the details of any of these projects really. It's like I have one slide for, some of the projects that I'm going to talk about. But if you're interested in knowing more details about any of these, feel free to talk to me, send me email. I will put you in contact with the students who are working on these projects, who will definitely be able to give you, and very happy to give you, discuss more details about those projects. Okay, so let's start with my current focus on systems research. So I will try to motivate this through some examples and applications. So think about an application like an augmented reality. I'm sure all of us are aware of what augmented reality is. Essentially, what we have is a video stream. And what we want to do is look at the objects on those in that video stream and be able to overlay some information on top of those objects, so that a user basically gets some additional information, enhanced information about the scene that is there in the camera. Okay. Now, if you think about this particular application, the first thing that we'll see in terms of the data that we have to process is that we are really dealing with a very large volume of data. Essentially a video stream, right? Continuously video frames are coming in. Some of this data, depending on the application, could be privacy sensitive, location aware definitely. And depending again on the application, the data could have only a limited lifetime. Now, from computation perspective, what we have to do really is capture this live video stream, and then segment this video stream into frames, and then possibly run some kind of object detection algorithm on top of these frames, And then once we recognize those objects, we have to basically retrieve the information about those objects, possibly using some kind of digital twins, and then overlay that information and then render the video. Okay. Now, from application requirement perspective, what we are dealing with is a very compute-intensive task, because object recognition is a compute-intensive task. And in general, any kind of video processing is compute-intensive. Most of these algorithms, like object detection, will be context-aware, and the nature of the application is that you have to be able to do this in almost real time. Typically a delay of at most 1 or 2 or 3 milliseconds. And then again, we may need some kind of privacy preserving requirements here. Okay. Let's look at another application. Think about a public space, something like an airport or a mall, where there are a lot of people walking around, and this place is equipped with different types of sensors, cameras, maybe infrared sensors, and our task is to identify people and essentially track people in this moving crowd, again, in real time. Once again, when we look at the type of data we have to process on, we are dealing with large volume of data. Data is coming from multiple sources. Location is specific, privacy sensitive, and limited lifetime. And the computation that we have to do will be something like face recognition, tracking of people, and in addition to some of the things that we were doing with augmented reality. And then the application requirements, again, are similar. Computation is definitely highly compute intensive, and then context awareness, real-time requirement, privacy preserving. Think about another application like a smart agriculture application. Okay. So here what we have is an agricultural field, and this field is basically embedded with different types of sensors, like air and soil moisture and temperature sensors. Maybe there is a drone that flies over this field and takes pictures of the field. And our task is basically to do some typical agricultural applications, like we want to irrigate the field in a smart way, so that we can conserve water, but at the same time make sure that any part of the field that needs water is actually irrigated. A smart fertilizer application, essentially detecting crop disease in time so that we can prevent them, locating weeds, so on. Again, we are dealing with large volume of data, multiple sources. In fact, in this case, the data that we are dealing with is coming from different types of sensors. And the data could have limited lifetime. So the type of computation we have to perform is some kind of pattern recognition, possibly, some kind of anomaly detection. And requirements, again, are compute intensive, and context awareness, maybe, requirement, maybe not strictly real time, but maybe near real time requirements. Think about a smart city. The smart city is embedded with all kinds of sensors everywhere. And what we want to do is manage different city operations in a very smart way, efficiently. So tasks like, optimal water energy distribution, traffic management, smart buildings, public safety. So again, the data is large volume of data, multiple sources, hybrid, location is specific, it has limited lifetime, privacy sensitive, and so on. Okay. And the computation that we want to do here is some kind of optimization. We have to run some kind of optimization algorithms, possibly do some kind of anomaly detection, context awareness. And the requirements, again, are compute intensive tasks, context awareness, near real or near real time type of requirement, depending on the type of operation we are looking at, and then privacy preserving. Okay. Now, the key question, so all these applications that we have looked at, they actually fall into this general area of what is nowadays called IoT environment, essentially an environment which is embedded with all kinds of smart sensors. So think about, air monitor sensors, environmental sensors, autonomous cars, robots, smartphones, smartwatch, health monitors, cameras, and so on. Okay. Now, these are basically static and mobile sensors. Some of these are located at fixed location, while others are moving around. And all these sensors are generating data in real time. And the goal, our overall goal, is to be able to collect this data and process this data so that we can provide some highly sophisticated personalized context-aware services to the users, to the end users in real time. Okay. And another very important requirement is that humans are part of this IoT environment. And so when we basically build any kind of application, any kind of system, we have to keep in mind that humans will be in this loop. So the key question that we are trying to answer here, and which is the focus of my research, is where to collect and process the sensor data to build these sophisticated context-aware services. So the first option would be to do on-site computing. What that basically means is that we have the sensor device. Why not connect the sensor device to a computing board and then do all kinds of computing there? There are some advantages, of course, to that. However, there are some obvious disadvantages. For example, we are basically dealing with limited resources in terms of power, in terms of CPU, in terms of memory, and then different sensors, are very different from one another. And so we have to deal with device heterogeneity. Okay. The other option is to ship all this data from the sensors to the cloud and then do all the computing on the cloud. Cloud, of course, we can assume that we have infinite resources there. So we don't have to worry about resources anymore. However, the limitations that we face there is all the data has to be shipped to the cloud, which could incur high latency, especially for some real-time applications the latency could be very high. Another one is all the data has to go to the cloud, which means it will consume a lot of bandwidth, network bandwidth. And then there is potential for privacy leakage, context may be lost. So there are those disadvantages. And so the third option, which is the focus of my research right now, is what is called edge computing, and the idea is very straightforward, really. The whole idea is to move the cloud closer to the users, to the sensors, to the place where the data is generated. Possibly, we want to move this cloud within one wireless hop. Okay. And so edge computing basically is a place where we have all kinds of applications like this. And what we do is we introduce a unit called edge server. And the data from these applications is basically collected sent to the edge server, as I said, which is within one wireless hop from these sensors. Okay. And the data itself, the edge server itself, you can think of it as like a data center, a mini data center in a box, and it could comprise of many different types of processing units. So think like CPUs and GPUs and FPGAs, any kind of special processing units. And with this, basically what we have is basically a 3-tier computing architecture. And the edge compute basically is the middle tier here. So on one end, you have the basically on-site computing. The other end, you have the cloud computing. In between, you have the edge computing. Together, sometimes this is what is called fog computing. So the advantage of edge computing is that because we are now within one wireless hop, so our latency is low. Bandwidth consumption is low because the data doesn't have to go all the way to the cloud. The edge server actually can serve as an administrative unit. So it can actually control who can access these sensors within an IoT environment. And then also edge server can be used to enforce appropriate security and privacy policies. In fact, edge computing has become a key driving technology for building sophisticated context-aware real-time applications in IoT or smart city service environment. Okay. However, there are some challenges. So building sophisticated context-aware applications at the edge is complex. Okay. Why is it complex? The first thing is that there is a lack of any integrated system-level support that applications can take advantage of. The computing resources that we are dealing with, the end resources. So think about all the sensors and computing boards that are there on site. There is a lot of heterogeneity there, and we have to deal with that heterogeneity. There is a dynamic nature of the computing environment where some sensors can come, some sensors will go, they are moving around. Some sensors can die because these are low-end devices. There is a lack of trust among the collaborating entities. And then there is minimal support for managing resources. And so these are some of the challenges. And so with that, our goal in this area is to develop and evaluate what we call a system level services. And the idea is that these system level services will be something that an application developer can use to build their application. Okay. In particular, what we are focusing on is providing support for building microservice-based architecture. Okay. Microservice, so when you look at this picture here, each of these boxes that you see, the gray boxes, these are basically what we call as microservices. Okay. Each microservice is basically is implementing a very simple functionality. So for example, as you can see, a face detection or a data collector, temperature data collector. And then you build an application by composing a set of these microservices that you actually need. Microservices typically run in an isolated computing environment. So, and operating system abstractions like Linux containers or Dockers. And then, what we need is a mechanism by which we can scale up and down these microservices, so depending on the type of load we have at that server. So within that area, I'll just go over some of the projects that we are working on. Some of these projects are, fairly at advanced stage. Some of them are beginning. So the first one is inter-container communication. So this is basically focusing on the edges that we saw between these microservices in our previous picture. So it turns out that this communication between these different microservices, that turns out to be a key bottleneck actually in determining the overall application's performance. That is the amount of time it takes to move data from one container to another container. And so the solution that we have developed, actually it's an ongoing project, is to use shared memory channels. Okay. So the idea is, to provide support for both bidirectional streams, something like what TCP, UDP kind of protocols provide, or provide publish subscribe kind of communication mechanism. And if our containers that are talking to one another, they happen to be on the same server, if they are co-located on the same server, okay, then we can basically create shared memory channels using setting host IPC to be true. Okay. And so basically in this case, the two containers can basically share a memory. And so they don't have to use the typical TCP IP kind of service for communication, which is very expensive. Okay. If the containers happen to be on two different servers, then our goal is to basically use the idea of what is called remote direct memory access, RDMA. And this part currently is under progress right now. Okay. And in order for the tools that we develop, in order for them to actually be usable, we want to make sure that these tools are compatible with Kubernetes. That is, Kubernetes is essentially a de facto tool for orchestrating containers in IoT environment or even in the cloud. And if you want our communication mechanism to be usable, then we want to make sure that it can be used through Kubernetes. Okay. Let's look at another project, what is called container graph. So the problem that we are looking at is, let's say this is one of my application that I have built. And each of these, again, boxes, rectangular boxes are microservices. And the problem that I have here is any kind of architectural level change that I want to make here. So for example, if I want to move from this configuration to this configuration where, I want to remove one of the microservice from this flow, and then maybe I want to introduce a new microservice in this flow, any kind of this change, if I want to do in Kubernetes, that will actually incur some kind of delay. Either your application will basically pause for a few seconds, and so we want to basically address that problem because this kind of architectural change is actually required in many different types of IoT application, and so the solution is basically to develop a tool that can enable this kind of architectural change, automatically without any kind of service disruption. So this is what we call as container graphs. And this basically provides support for dynamic container instantiation and orchestration. So what it does is it provides support for dynamic instantiation, removal of microservices. So you can remove a microservice or introduce a new microservice. Okay. You can alter the communication pattern among microservices. So basically move maybe one arrow from here to here to maybe move that arrow to over here. Okay. And the current application operation or the data flow remains undisturbed. That is, the applications do not incur any kind of disruption. Okay? There is no application downtime. Okay? Once again, we want Kubernetes compatibility. So this is another project that right now, this project, basically we have a standalone prototype of this, but we are currently exploring integrating with Kubernetes. Let's look at a third application. This is actually a very new application, a smart agriculture application. And this is an application that, research that I'm doing with some of my collaborators in India. And the goal here is to develop an end-to-end LoRa-enabled edge-based infrastructure for smart agriculture, both in India and USA. Okay. And so the prototype that we are trying to build is comprised of three different layers. The lowest layer here is what is called sensing layer. Middle layer is edge computing layer. And then the top layer is basically the cloud computing layer. So the sensing layer, the goal of the sensing layer is to basically sense this agricultural field parameters. So I talked about smart agriculture application earlier. So the idea here is to put different types of sensors, and then the sensor data from those will be communicated to the edge server. Through in our case, we are using LoRa and LoRaWAN. What this protocol provides is a way by which you can send data with one wireless hop over a few kilometers. Again, depends on the environmental conditions, but you can still send the data over like a 1 kilometer, 2 kilometers, much larger than a Wi-Fi would do. Okay. So that's basically the idea here at the sensing layer. Then fog layer is basically what we discussed earlier. Here we want to provide support for latency sensitive services. In particular, the type of services we are looking at are actually three different services. The first one is basically detecting animal intrusion, especially in India. That actually is the #1 concern of the farmers. That is, in late evenings and nights, animals intrude into the agricultural field and they destroy the crop. And so if we can basically develop any automated way by which we can detect that there is an animal intrusion and possibly alert the farmers, or even do some kind of actuation to drive away the animals. Another one that we are looking at is basically detecting fires in the agricultural field. This is an issue in agriculture fields in US, where fires is a problem. And so can we detect fires in advance? Can we detect conditions that are going to be contributing to a fire in the future? And then the third one is smart irrigation system. And then the third layer is basically the cloud layer. It's a complex, basically this is where we want to do complex compute intensive decision-making tasks. Some tasks that basically are not latency sensitive, and then possibly also for long-term data storage and visualization of your data. Okay. So this is basically an application that we are building, which is a direct application of the edge computing research that we are doing here. There are many other applications. I'll quickly go over. We have a distributed scheduling research project, which is basically the idea is to develop a scheduler that can distribute our computing tasks across different kinds of computing devices. That is, including your end devices, as well as different types of processing units within your edge server, and possibly into the cloud. Okay. The challenge that we have here is how do we keep this overhead of making scheduling decisions low, so that doesn't become the key bottleneck. Okay. Another project would be, actually we have multiple projects that are dealing with privacy issues at the edge. And as you can imagine, in an IoT environment, in a smart city environment, privacy is a key concern. And so we have some projects in that area as well. Okay. So that's basically what I would say about my systems research. And again, before I move on, a lot of students have contributed to this, some of the projects that I talked about. The top one basically lists the students that I have at the moment working with me. We have 4 PhD students and 2 master's students who are working on various projects within this. And then these 2 students are basically my former students who have graduated, and they are faculties. And their PhD research is what actually, about, I would say like 10 years back, their PhD research is basically created all this whole research direction. Then there are other students who have now graduated, who worked on these projects. These are all PhD and master's students. Okay, so let me move on to the next area, which is social computing. So I'll start off with the first topic within this social computing, which we call as cyber safety. Okay. And when we talk about cyber safety, essentially think about any kind of problematic issues that arise when you are basically surfing the internet. Okay. So things like cyberbullying, right? So I mean, if you are using some kind of social media, cyberbullying actually is common, especially in middle and high school students, right? Or you might encounter some kind of obscene, content, right? Or you're exposed to misinformation or propaganda and so on. Okay? And so the goal, our research goal within this cyber safety research is to develop tools that can automatically detect these cyber safety issues. So they can automatically detect, for example, incidents of cyberbullying. Okay? Our goal is also to assess their impact on the end user. That is, how the end user is actually getting impacted by this, by this misinformation, by this propaganda, and then hopefully develop techniques by which we can mitigate some of these negative impact. Okay, so let me talk about a few projects within this. One of the currently ongoing project is Radicalizing YouTube. Okay. And so here what we want to do is we want to investigate how YouTube's recommendation algorithm plays a role in online radicalization via surfacing extreme content. Okay. In particular, what we have done is we are investigating prevalence of, we are doing this in the context of Arabic YouTube videos right now, but the techniques that we are developing are applicable to any kind of YouTube. So basically we want to investigate the prevalence of religiously intolerant Arabic YouTube videos and the tendency of these platforms, these YouTube platform, to recommend these videos, the extremely religiously intolerant videos, extreme videos, okay? And more importantly, how these recommendations are affected by their demographics and watch history. And to do that, and again, the idea here is to give you the methodology, type of things. I'm not going to go over the details, but the methodology. In fact, all these projects, the major part of the research is actually simply collecting the data. How do we collect the right kind of data? So in this case, we used a YouTube API to collect the right kind of videos by providing appropriate keywords. Then we used crowd workers basically to acquire annotations for a subset of these videos to identify the ones that promote religious hate. For each video, then we collected the top 4 recommendations. As you watch these videos, what videos get recommended, and we went like 5 levels deep. And then we also investigated the effect of personalization, because we know that in YouTube, the videos that you get recommended depends on your surfing habits in the past. And so in order to understand the effect of personalization, what we did was we carefully crafted 8 different user profiles, with different characteristics, basically we basically analyzed all the videos that could get recommended for these different user profiles, and then we have analyzed them. If you're interested in this kind of work, this paper has recently been accepted, and I can put you in contact with the student who is working on it to give more details about it. Let's look at another project, which is also ongoing project right now. It's a Snapchat as a lens for public health. And so here the goal is to investigate how exposure to food snaps impacts eating habits of the users. So the idea here is that, when you look at these snaps in a Snapchat, often a large number of those snaps will be related to food items, like the restaurant pictures or food pictures and so on. Okay? And the research question that we want to investigate is that, do they affect the eating habits of the end users? Okay? And to do that, what we did was first, again, we collected Snapchat snaps from users in 3 different countries. Okay? And then we categorized these snaps. We used automated way of identifying what kind of snaps those are, identified the food related snaps. And then in order to understand the impact, we actually conducted user studies where we actually developed our own algorithm for Snapchat, where we recruited users who would basically watch some of these snaps, and then we basically made observations about what kind of food they are ordering and other things. So that's basically the idea here, is to basically see if there is a relation between what you're seeing on your social media to some of the epidemics that we have in our society. Like in this case, the obesity. Is there a connection? So that's what basically we are investigating in this project. Another project is hate speech in Arabic social media. Okay. So it turns out that religious hatred is a serious problem, and the goal here is, this is actually a project that we have already completed. So this is a quantify and characterize religious hate speech on Arabic Twitter space, and then develop classifiers to automatically detect religious hate speech in social media, and to develop tools to detect bots involved in spreading religious hate. Okay. In this case, also pretty much similar methodology. We first collected a large data set of Arabic appropriate tweets, analyzed those tweets for appropriate hate content. We got those tweets labeled, and then develop classifiers to detect these hate, and then basically tools, to detect these bots also in Twitter space, and then see the role of the bots in spreading of this religious hate. Very interesting results, actually. If you're interested, we have published a paper on this topic as well. Yet another project is content deletion and moderation on social media. So social media platforms, they strive to moderate their content by either censoring the postings, or demonetizing, or removing the posts that allegedly violate their community guidelines, right? So we see this all the time. Sometimes these social media, they will put some kind of labels on these posts, right? Or sometimes they will outright remove them from the platform. So the issue is that some of these practices could be met with resentment, anger, and in some cases violence. Actually, if a user posts a YouTube video and the platform takes that down, there have been cases where that has actually ended up in violence. Users also sometimes delete their posted content for various reasons, one of which is actually regret. Like you may post something on the social media, and then a few minutes later, you may realize, oops, that's not what I posted. You delete it, but as you know, once you have posted something on these social media, they are basically go viral. And so the research goal here is to understand the characteristics of the posts that get deleted, and then an ability to predict deletion before posting the content. That is, the idea is that, just before you are about to post your next tweet, or just before you are about to post your next YouTube video, is it possible that the platform can warn you that, there is a high chance that, you may regret posting this. It's just a warning. And then you can either, heed to that warning, or maybe think before posting. That's the idea here. Okay. So again, this is a project that we have worked in the context of YouTube. And we have a paper published on this. If you are interested in looking at it, the student working on this is also here, so she can talk to you. Okay. So in this case, basically, again, we monitored about 74,000 YouTube videos. One of the issue here, as I said, one of the big challenges is data collection. In YouTube, once a YouTube video is deleted, it's no longer available. There is no way you can actually get to see that video. So what we really have to do is monitor the video from the time it gets posted until it's get deleted. So there is a whole process by which you have to follow in order to collect deleted YouTube videos. We did a detailed analysis to distinguish deleted videos from undeleted one. Developed classifiers to predict videos that will get likely get deleted. In fact, the classifier that we actually developed, ultimately it detects, it gives a warning with something like a above 85% accuracy, that the video will get deleted. Okay. So the students who are working on these projects are Nuha and Maram. Both of them are PhD students. So if you're interested in any, talk to me, and then I can put you in contact with some of these students. Okay. Let me talk a few things about democracy and technology. So it's not a surprising fact now, that there is an impact of technology on our democratic process. In fact, there is a serious mismatch that is gradually developing between these two seemingly unrelated issues, that is the penetration of science and technology into all aspects of our life, and the democracy as practiced throughout the free world. And the question that we are asking here is, could these technologies endanger the foundations of liberal democracy? And so the goal of our research, high-level goal really here, is to strengthen democracy through technology. So this is one of the projects that I'm going to talk about, and this is basically some of the publications, some of the things that were published a few years back, which showed that in 2016 election, Russian bots basically tried to influence the election. Okay, and so the project that we worked on is basically to evaluate the impact of Internet Research Agency. IRA is basically the agency in Russia which basically deployed these bots with the aim to basically disrupt the US election process in 2016. Twitter actually has released all this data, so they have basically released the entire data set of the suspected bots along with all the tweets that these bots sent. Okay. And so the question that we asked here is, so Twitter has of course released the data from the bots. And our question was, did these bots, whatever tweets they sent, did it end up changing the attitude of the end user? That is, if I'm a user, I came in contact with some of the tweets that these bots sent, did it change my behavior? That was the question that we asked in this research. Okay. And in order to do that, again, as I said, data collection is the major part of this research. In order to do this research, we had to first identify who are the actual users, the normal users, who came in contact with these with the tweets that these bots sent. That's basically one of the major part of that research. And then once we identified those users, then we basically looked at their behavior before they came in contact with the bots, and then their behavior after they came in contact with the bots. Okay, and we basically found some very interesting results there, which basically showed that indeed there was actually a change in the behavior of the user. Again, this paper is also published. Okay, so if you are interested in looking at this work, I'll be happy to provide you with the reference. There are many other projects, in the interest of time, I'm not going to talk about the details, but there are many other projects that we are working on. This is a topic that we are very interested in pursuing. There is basically one project is characterizing the level of toxicity across different social media platforms. Another one is essentially analyzing behavioral change of users after exposure to misinformation. We all know that there is misinformation all over the place. The question again is, how does that impact the end user? That's the question. Understanding how readers determine the legitimacy of online news articles in the era of fake news, right? So there is a lot of fake news in the in online systems, and when we read the news, there are some news that we believe, while other news when we read it, we know that this is not true, right? And so the question is, how do users make that decision? That's basically the question in this third research direction. So this is actually a project that I'm working with, 3 faculty members from our department, Professor Ray Khan, Professor Tamara Lehman, and Professor Christine Liu. And then several students have worked on these projects. Jason was our PhD student who has graduated now. And then Rhett and Yi Chen, they are here right now. And then Upasana and Shreyasa, they have just graduated. Okay, the last topic is socio-technical system. In some sense, socio-technical system is basically the combination of my research efforts, both in the area of social computing and in the area of edge computing. Okay. So the idea of social system is nowadays the communities in US and essentially around the world, they are entering a new era of transformation in which residents and their surrounding environments are increasingly connected through rapidly changing intelligent technologies. Right? So a socio-technical system essentially refers to the interrelatedness of social and technical aspects of a community. Okay? So this interaction of social and technical factors that creates the conditions that are hopefully beneficial to the community. And so the goal that we have our research goal is to basically exploit this intelligent technology that is, embedded in our communities today, and the goal is to exploit this technology to essentially improve the health and well-being of the end users. Okay, I will motivate this through one project that we are right now working on, which is empowering environmental justice communities with a smart and connected technology. Okay, so this is a project that a large team actually, there is a technology team, there is an environmental engineering team, and then there is a social science team. We are basically studying two planned built environment disruptions in Denver. The two environments are basically, one is called C70 project and the other is NWC redevelopment. Okay. So the C70 project is basically a 10-mile stretch on I-70. It's essentially just east of I-25 as you go on east on I-70. And they are basically, if you have ever driven on that highway, you will know that there's a major construction going on in that area. And then the National Western Center redevelopment is doubling the complex footprint and land acquisition. Okay. Now, the communities that live around these areas, they tend to be, so these, in this case, the three communities that we have identified that are very in close vicinity of this area. These communities are Globeville, Elria Swansea, and Cole. Okay. Now, the characteristics of these communities happens to be that these are what are called environmental justice communities. Okay. What that means is basically they have low socioeconomic status. There is a high unemployment rate, typically less than high school education, mostly Hispanic in this case. A lot of these population doesn't speak English. Okay. And this whole area is actually has a long legacy of environmental contamination. Those of you who have been in Denver, you will know, if anytime you drive, you will notice, that there's a major environmental pollution in that area. Okay. This is the picture that shows that area. This is basically the I-70 that is going east-west, and then this is I-25. And just east of that I-25, is where these communities are located, and this is where the major construction is going on. Okay. So the project that we have is to build a socio-technical system, which is comprised of these different types of environmental sensors, smartphone platforms, and a data analytics server equipped with predictive modeling and visualization, with a goal to first understand the personal environment, individual well-being, and social relations of environmental justice communities affected by a major planned disruptions in their built environment. So the idea here is basically, how do these constructions impact the health and well-being of the community that is in close vicinity of these sites? Okay. Second one is basically, once we understand this, can we basically mitigate some of the negative impacts of these disruptions? Can we do something about it? And then the third one is basically to equip policy and decision makers with information in advance about potential negative impacts of upcoming disruptions, because the type of disruption we are talking about is pretty well planned. Actually, think about a new bridge being built or a new smart city being developed, right? So these are all very well planned disruptions, and so there is generally plenty of time in advance that these decision makers can actually use to put in appropriate safeguards so that the communities in the vicinity do not get negatively affected by these disruptions. Okay. And so we have basically done a lot of work in this area. We have put a lot of environmental sensors in this area. We have developed 3 different smartphone applications. We have basically provided personal air monitors to some of the community members, and we are basically collecting a lot of data. And at the same time, we are also developing some intervention mechanisms to mitigate the negative impacts. From technology perspective, we have developed 3 different smartphone apps. Pure Motion app basically is an app that essentially collects the wellness data of users on a regular basis. Pure Connect is an app that provides some kind of community building among community members. So it provides a way by which the community members can share their concerns. They can communicate their concerns to the appropriate authorities. They can ask questions, whenever they have any questions about what is going on in the surroundings. PureNav is another smartphone application that provides a navigation app. In fact, when we talked to the community members, we held actually several focus groups actually in this community. And the top concern of these community members is basically the disruption in their daily communication, the transportation, commute. And, and so basically, based on the data that we have collected, we have developed this transportation application. We are calling it PureNav, essentially a smart transportation application, which actually goes much beyond what your Google Maps or Apple Maps, those things will provide. Okay. And also, as I said, we have active users with community members with personal air monitors, and the whole project basically has a timeline where we are deploying these our sensors, our apps over 4 different what we called as cohort. So two of them have already been done: winter cohort and the summer cohort for winter 21 and summer 22. And these two are in each cohort, basically about 100 community members are participating. They basically are using our apps, and then they're carrying these personal monitors, and they're providing us with some very, very useful data. And then at present, basically, we are introducing these interventions. And then, starting in October, actually, mid-October, our next deployment will happen where we will try to understand the impact of these interventions. Does it actually change anything? And then later on, again, we'll do something similar with in summer 23. Okay, so this is actually, again, as I said, it's a large team. The faculty members, the other faculty members who are involved, this is Professor Shelly Miller from Environmental Engineering, and then Professor Esther Sullivan. She's a professor of sociology from CU Denver, and then Nicholas is a postdoc researcher in this project. And then we have, this is our technology team. This is basically the students who are from our department. We have 2 PhD students, then we have 2 master's students, and then 1 undergraduate student working on this project. Okay, and so this is just a technology team. We have students working from environmental engineering team. We have students working from social science team, and so it's a fairly large project. Okay. So that's basically a simple preview of the type of research I am doing, and I am always looking for some really good students. PhD students who can do master's thesis, MS independent study, undergraduate research, undergraduate thesis. I'm looking for students in pretty much at every level, and I have to say that all the students who have worked with me, they have found this the type of project that I do very rewarding. So if you are interested in any of these projects, please feel free to send me email. I will respond to you. I will put you in contact with some of the students who are working on these projects. And based on what I have described so far, if you have some ideas, that I may not have covered in my presentation, but if you think that's related to something that I'm working on, please come and talk to me. I will be very interested in hearing from you, and we can definitely move a project forward. Like, as I said, all these projects that I'm talking about, they all originated from students, and over time, they have developed and matured. So please come and talk to me about this. Okay, so that's the end of my presentation. Thank you. And if you have any questions, feel free to talk to me. As I said, definitely send me email. I will be, or just stop by my office, and I'll be very happy to talk to you about any of these projects or any other future research that you're interested in.
Thank you, Shiv. Anyone has any questions, you can unmute yourself and ask at this time, or you can even put it in chat. I think unmuting might be better so that Shiv can hear other voices too. Chetan, go for it.
Hey, that was a great session. So I was actually particularly interested in this accelerated container communication. So what kind of changes are being done? Like, are the changes being done in the context of Kubernetes, or are you developing some sort of a different library? And also, I have another question about RDMA. Does it require any hardware support?
Yeah. So the first thing is that what we do is we have developed this tool for inter-container communication that essentially uses shared memory channels. So it creates shared memory channel. It puts the containers in, contact with one another, establishes that, and then we have to actually modify some code within Kubernetes so that these tools can be used from Kubernetes. So that as a because you're using Kubernetes for any kind of container orchestration, and so as a Kubernetes user, you can basically use this tool instead of the standard container communication tool, and then you'll be able to build your application. Okay. Now, the other question about the RDMA. So there is RDMA support, actually, different types of RDMA support. One is actually where you require special hardware. However, there's also RDMA that is actually over converged Ethernet. And so you don't need actually any kind of hardware, special hardware, if you are using that kind of support. So recently, the Intel and there is whole consortium actually that they have basically developed this whole protocol that works over Ethernet that can provide RDMA support.
Okay. So yeah, thank you. So I just had a follow-up. So what are the kind of challenges that you faced when you wanted to extend Kubernetes with this new
Right.
communication?
Yeah, right. So definitely, I mean, that's one of the big, it's easier said than done, as you can imagine. Like Kubernetes is, of course, a large piece of software, and making any changes, you have to first understand the Kubernetes code, right? In this case, what we had to use is something called custom controllers, that basically allowed us to incorporate, basically we had to provide information about, which containers want to communicate with one another, information about the shared memory channel through the YAML file that you provide to the Kubernetes, and then the Kubernetes through custom controllers is able to, read that file and then use our tool instead of the standard container communication tool. Yeah, it's a process, but like any other systems research, any systems research that you do, you will not do it in isolation, right? I mean, you always start from somewhere, and so that's the way it is. It takes some time to get used to it, but it's a rewarding work, really.
Okay. Yeah, that's interesting. Thank you.
Akshay?
Yeah, thank you, Professor. It seemed like 3 different pre-research advising sessions just combined into one because of the variety of work that you're doing. So my question was firstly that because your work is sort of overlapping with a lot of different fields, like in social computing, it's overlapping with security and cyber safety. In other areas, in the edge computing, it's overlapping with agriculture and different IoT devices. So how much does one need to have that sort of knowledge to get into research with your work?
Right.
Yeah,
So
that's the first part
right.
of the question.
Yeah, that's a good question, actually. One thing I would say is that typically, if you're interested in systems research, right? I mean, something like edge computing, I highly encourage students to take my course, which is basically the advanced operating system and the distributed system. I cover many of these topics actually in those courses. One of the key requirement, not a key requirement, but typically I look for, that you have experience with using containers, for example, right? That you can deploy containers and work with them, orchestration, Kubernetes orchestration, and those kind of things. That's something that I expect students to know. There are many other courses, not just these 2 courses. There are other courses that also teach you, like data center scale computing, that basically also covers container orchestration and so on. So yeah, so that's one thing, definitely. But in general, basically a good systems background, knowledge about operating systems or network systems, that's another course which is very useful for the type of research that I do. So that's basically for the system side. For cyber safety and in general social computing, I am basically a user of machine learning algorithms. So I'm not really developing new machine algorithms. I'm not really developing new object detection algorithm or a new way to develop some classification models or anything like that. The idea is to use these libraries that are already available to solve the problem, the research question that I have, So the thing that would be very helpful there is if you are familiar with how to use these machine learning tools, different libraries like TensorFlow and PyTorch and those kind of libraries. If you can use them, if you can use them to build models, given a set of data, can you basically, given a problem, can you build a model out of it? That's the type of background would be very, very helpful for this kind of research that I'm doing. But the key here is my research always starts with a research question, really, not with the technology that I'm going to build, but it's always with a research question. Why is it interesting? That's the first thing that we have to ask, application or whatever. And then from there, basically you decide, okay, this is the research question. This is the question that we want to answer. And then what is it that now we need to answer that research question? And, like, for example, in that project on, socio-technical system, I'm actually using both the machine learning algorithms as well as, my edge computing background, right? Both of those are used in it. So,
Yeah, that makes sense. I have a follow-up question regarding, because you're doing a lot of research that is very specific to a domain, let's say agriculture, or I saw one image where you were trying to classify people. I mean, you were trying to tag people, sort of. So how much of the research that you do or the kind of products that you build really depend on the kind of requirements that drive them? Like the requirement is very specific, right?
Absolutely. No, requirements are not specific. The idea, again, the systems research is always based on what applications you want to support. And the goal here is what sometimes we call as identify the right system abstractions, And when we say right system abstraction, what we are basically looking for is system services that would be usable for building a wide variety of applications. So in the beginning, when I presented, like a series of applications, those applications may look very different from one another, but at the end, from systems perspective, their requirement is very similar, actually, that they need efficient inter-container communication, they need dynamic orchestration, that's the idea, So the idea is to take these applications and motivate your system design.
Okay, so it's basically, it may seem very different from the application perspective, but in the background, what you're trying to build is a very general solution which can be applied to multiple places.
Correct.
If I get it correctly. Okay,
yes,
that makes sense.
Yes.
Okay, thank you so much.
No problem.
Oh, you have your hands. Okay, go for it.
Yeah, Professor, I had a question. Like the shared memory between containers sounds interesting. Kind of solves the
Right.
So I was wondering if it is being developed in the broad sense or only to edge computing systems.
I see. So shared memory is actually we are developing this in the context of containers. And containers are actually used both. Of course, they are the driving technology for edge computing, but containers are actually popular for cloud computing as well, right? I mean, if you have done anything in the cloud, you'll probably have used containers there. So the solution is applicable definitely to the cloud as well. Our work is motivated by applications which are at the edge, but the tools that we are developing are certainly applicable to applications that we will run on the cloud.
Okay, got it. So a follow-up question. So will it be like a separate protocol that you're implementing, or something that is underlying? Like, for example, currently what I know is usually containers use APIs to communicate. So
correct.
Does it continue to use the API, but underlying the system changes as it?
Right. So they will continue to use the API. What we are doing is basically, you can imagine like building some kind of a wrapper around those API, so that with those wrappers, instead of because underlying that API, it is basically using a TCP/IP protocol, right? Network protocol, TCP/IP protocol, which is what basically introduces the performance overhead, And so the idea is to put some kind of wrapper that would basically, when you invoke that API, instead of using the TCP/IP underlying, it will use the shared memory channel. So that's the, and so ultimately we want to basically release these things as libraries. where people can install these libraries, link those libraries, and then be able to use this tool, hopefully without making any changes in their application. But that's something that we have not yet achieved, but that's the final goal, really.
Oh, I see. That sounds very interesting. Thank you.
Okay, thank you everyone for your questions. We're right on time. And as always, Shiv, it's so impressive. You have so many different projects going on every time. I really enjoy your pre-research sessions. So thank you so much for your time today. I'll be sharing the recording with students who couldn't join today, and I'm sure they'll be reaching out to you. Thank you once again.
Thank you.
Thank you.